In this series of videos I'm going to speak about the method of characteristics, which we've already met in the lectures, and it's the method that we've used to solve first order linear partial differential equations. Now hopefully these videos will be useful when you come to revise and also when you come to do the assignments. I'm going to split it up into three different videos corresponding to these three cases. So the first case is going to be this one here, where we have constant coefficients. So the terms that are multiplying the partial derivatives u sub x and u sub y are going to be constants. Then in two other videos I'm going to look at the case where a and b are functions of x and y, so we have variable coefficients, and finally the most difficult general case where we also allow for there to be some term involving u without any partial derivative, and for there to be some right hand side which is a function of x and y. In this video I'm just going to consider the first of these cases. So let's jump in by considering one specific example, one choice of a and b here, and let's have a look at this case here where a is 5 and b is 2. So our partial differential equation is 5 times the partial derivative of u with respect to x plus 2 times the partial derivative of u with respect to y equals 0, and we've also been supplied with a boundary condition that says that when x equals 0, then the function u along that line is going to be given by sine y. So what can we say about this equation? Well, it's linear because all we're doing to u is multiplication by constants and differentiation with respect to x and y partially, and those are all linear operations. It's first order because we only have first order derivatives here. It's homogeneous because once we've put everything that involves u onto one side, then we've got 0 on the other side, and it also has constant coefficients, 5 and 2. So the first step when we're dealing with a problem like this towards solving it is to rewrite it in a particular form. And this will allow us to use arguments involving directional derivatives. So let's just recall what this notation all means. So here we've got the gradient of u. So what does that mean? Well, that is just the vector whose first component is the partial derivative of u with respect to x, and whose second component is the partial derivative of u with respect to y. And then we have a dot product here, so let's just recall what the dot product does. Well, it multiplies the first component of each vector, so this is going to be 5 times ux, and then it adds on the second components multiplied by each other, so this is going to be plus 2 uy. So if we expand this dot product, we'd have 5 lots of ux plus 2 lots of uy, and if we look back at our original equation, that is exactly what we had before. So we haven't done anything fancy here. All we've done is we've rewritten the PDE. And on the right hand side, of course, we've still got 0 just as we did before. So why have we done that? Well, that allows us to say things about the directional derivatives. So if we have a vector that is dotted with a gradient, then that is the definition of the directional derivative of the function that we have the gradient of, so in this case u, in the direction of whatever this first vector is, and in this case it's 5, 2. So we can say, from having rewritten the equation in this form, that the directional derivative of u in the direction 5, 2, in other words 5 along in the x direction for every 2 we go up in the y direction, is equal to 0. And if we have a derivative in some direction that's 0, then that implies that the function itself, u, must be constant along any curve that is in that direction, 5, 2. I'm now going to cheat a little bit and show you what the actual solution looks like. So jumping forwards a little bit. So we've made this claim that in the direction 5, 2, along these characteristic curves, which I've plotted here in black, that the solution remains constant, that u remains constant. Now, here's the plot of u, a surface plot, because u is a function of x, which is along this axis, and y, which is along this axis, and the height of this surface is just the value of the function u. Now hopefully you'll agree with me that these black characteristic curves are lines along which u is constant, because they're just flat horizontal lines. Now you can see that this has got a sinusoidal shape. That's because of the boundary condition, but just focusing on the characteristic curves, they are curves that if we look down from above we can see that they're in the direction roughly 5 along for every 2 we go up, and u is constant along each of those. So for each characteristic curve, u takes a particular value, and if you keep going in the direction 5, 2, then u stays as that constant. So here's a better plot of u looking down from above, and you can see from this that these really are completely parallel lines, and if you work out what their slopes are, then you'll find that if we go 5 units along in this direction, 2 units up in this direction, then these are this is the direction in which u remains constant. So this is what I mean by the direction 5, 2. I mean 5 along in the x direction, 2 up in the y direction. So the next question is going to be, can we find equations for these curves? Well, we can see from this picture that the gradient of each of these lines, dy by dx, is going to be the change in y over the change in x, because they're straight lines. So that's just going to be 2 over 5. So we're looking for lines with dy by dx equals 2 over 5. So that's a very simple ordinary differential equation that hopefully we can solve, because all we need to do to solve that one is integrate both sides with respect to x. So if we integrate the left hand side with respect to x, we just get y, and if we integrate the right hand side we get 2 over 5 times x plus a constant, plus c. And hopefully that is very clearly the equation of a straight line with slope 2 over 5. Now the interpretation of that constant c, which is arbitrary for the moment, is that that is the y-intercept. So each of these different lines that we had on our picture before, along which u is constant, is just corresponding to a different value of c. So if you change c, it just chooses which characteristic curve you're on. Okay, so what now? Well, we say that along each of those curves we know that u is constant, as we've said many times, and so we can deduce that the value of u is going to be a function just of that constant, and we've got an expression for the constant c, because we can just rearrange this equation here to get that c is y minus 2/5 of x. And so rather than writing f of c, we can write f of y minus 2/5 of x, where f is a function of just one variable. So this is the general solution, what I've got written in red here, of the partial differential equation. But we also had a boundary condition, so let's have a look at how we can apply that to find what this function f must be. So the boundary condition was this one here. It said that when x was 0, we should get the function sine y. Okay, so in order to apply that, what do? Well, we say that u, when x is 0 and y is y, that is just going to be like sticking 0 into these expressions for x. So u of 0y is f of y minus 2 over 5 times 0. Well, 2/5 of 0 is 0, so this is just f of y. And the boundary condition says that that should be equal to sine y. Okay, so we found what f is, because f is just the function that takes y to sine y, so f is just the function sine. Therefore, when we've got the general solution here, we found out what f is, so let's write it in. So we found that u of x and y is equal to sine y minus 2 over 5 x. And that's the answer. That is the solution. That is the picture that I showed you earlier of that surface. So that's this guy. And that's the method for finding out what this surface is. So in the next video, we'll look at the case with variable coefficients.